All right, let's dive into the world of LLMs, large language models. We're going to try to help you get a grasp on these powerful tools and how NVIDIA NeMo can be used to fine-tune them.
Yeah, and not just any fine-tuning.
Right.
We're talking about parameter-efficient fine-tuning, or PEFT for short. It's a game changer when you're dealing with models with billions or even trillions of parameters.
Yeah, we're talking serious computational muscle here.
Yeah.
So what exactly are large language models? I mean, the name kind of gives it away, but
Well, you can think of an LLM like a superbrain. It's trained on massive amounts of data. We're talking billions, even trillions of words. And this lets them understand and generate human-like text in response to different kinds of prompts.
okay, so like if I asked it to write a haiku about cats, they could do that.
Absolutely. Or it could translate that haiku into a dozen languages, write a blog post about the history of haikus, or even generate code that analyzes the sentiment of different cat-themed poems. It's astonishing, really.
Color me impressed. So what's the secret sauce behind these LLMs? How do they actually work?
The key ingredient is deep learning, specifically a type of neural network called a transformer.
Transformers, like the robots.
Not quite, although they are pretty transformative in the world of AI. The key innovation in transformers is something called self-attention.
Self-awareness for robots. What does that even mean in this context?
Okay, so think about how you read a sentence. You don't pay equal attention to every single word, right, Trey?
Right.
Some words are more important. Their meaning depends on the words around them.
It's context.
Exactly. Self-attention allows the LLM to do that same thing. It figures out which parts of the text are most important and how they relate to each other, just like we do.
So it's not just processing words one by one, it's actually understanding the relationships between them. Fascinating. But I've heard there are different types of transformer models.
There are encoders, decoders, and encoder-decoders.
Wow, a whole family.
Encoders are like the understanding part. They figure out what the text means. So imagine an encoder reading a movie review to figure out if it's positive or negative.
Got it. Decoders are the creative types then.
Yeah. They're the generative part. They would be the one writing the review.
Okay. And what about those multi-talented encoder-decoders?
They're the translators. Think of them taking English, understanding it, and then generating, let's say, Spanish. Basically, they handle tasks that involve both understanding and generating text.
Okay, that makes sense. Now, everyone's been talking about GPT-3, but I know there were earlier versions. What's the family history here?
Yes, the GPT saga. It all started with GPT-1 back in 2018. It was revolutionary for using that transformer decoder for language modeling.
And then came GPT-2 in 2019. Bigger, better, bolder.
Absolutely. More parameters, better text generation.
And finally, the big kahuna, GPT-3, in 2020. A whopping 175 billion parameters.
Right. Trained on this massive data set of text and code, it was a huge leap forward. It can write different kinds of creative content, answer questions, generate different text formats. It's remarkable.
That's impressive. But I imagine training and using these massive models takes a lot of computing power, right?
It does, and that's where NVIDIA NeMo comes in. It's a framework specifically designed for these really big models.
So NeMo is like the ultimate LLM gem,
Yeah.
helping them flex their computational muscles.
You could say that. It's a toolbox for building, customizing, and deploying these LLMs, even ones with billions or even trillions of parameters.
What makes it so special? Why NeMo?
Well, first, it's optimized for performance. We're talking about training massive models here. Efficiency is key. Plus, it has user-friendly APIs, so it makes working with these complex systems much, much easier.
So even a non-expert could use it.
Exactly. And on top of that, NeMo has this incredible library of pre-trained models that you can use. So it's like a head start.
Sounds like a dream come true for researchers and developers.
Yeah.
So could you use NeMo to build, say, a virtual assistant that can really understand complex requests?
Absolutely. Or maybe a super smart chatbot for customer service that can handle a wide range of questions. The possibilities are pretty much endless. And one of the things that makes NeMo so powerful is its ability to scale. It can use multiple GPUs, which means you can train these massive models way faster.
Okay, that's some serious parallel processing power. And speaking of power, I've heard about NeMo Megatron. What's that all about?
NeMo Megatron, that's the ultimate training ground for the really, truly colossal LLMs, the ones with potentially trillions of parameters. It uses techniques like data parallelism, tensor parallelism, and pipeline parallelism to train the model across multiple GPUs or even multiple nodes.
Wow, I'm getting flashbacks to my computer science classes.
Yeah.
What's pipeline parallelism again?
Okay, imagine you're building a car on an assembly line. Each worker has a specific job, and the car moves down the line.
Right. Gets a little more complete at each stage.
Yeah, it's similar with pipeline parallelism. We break down the model's training process into stages, and each stage is handled by a different part of the system. It lets us train models that wouldn't fit on a single GPU.
Like a well-oiled machine, each part working together. What kind of models can NeMo Megatron handle?
Pretty much all of them. GPT-style decoder-only models, T5 BERT-style encoder-decoders, BERT-style encoder-only models, and even the newer retro-style decoder-only models. It doesn't really matter what architecture you're working with, NeMo Megatron can handle it.
Sounds like it can wrangle even the most massive LLM. But training a massive model from scratch every time sounds incredibly time-consuming and resource-intensive.
You're telling me! That's why we have this thing called parameter-efficient fine-tuning, PEFT, fine-tuning with superpowers.
Okay, I'm intrigued. How does it work?
It's all about strategy. Instead of retraining the entire model, we freeze most of the model's parameters and just focus on fine-tuning specific layers.
So instead of repainting the whole house, you just touch up the areas that need it.
Exactly. It saves so much time and resources. Plus, it helps preserve the model's general knowledge while letting it specialize.
That's really clever. So walk me through the different PEFT techniques. What are our options?
One popular one is using adapter layers. Think of them like add-ons or plugins for your LLM. They're small, task-specific modules that get inserted between the pre-trained layers.
So like giving it a specialized toolkit.
You got it. And these adapters can be trained on the new task while the original model stays frozen, so it keeps its general knowledge but becomes an expert in this new area.
All right, adapter layers, check. What else is in the PEFT toolbox?
Well, we'll dive into those in part 2 after we give our listeners a little break. Welcome back. Before the break, we were talking about PEFT and how it can make fine-tuning LLMs way more efficient. Let's dive into a couple more of those techniques.
Sounds good. We talked about adapter layers. What else is there?
We've got prompt tuning and P-tuning. They both focus on guiding the LLM without that massive retraining.
Guiding it, giving it instructions.
In a way, yeah. With prompt tuning, we use these things called soft prompt embeddings to kind of nudge the LLM in the right direction.
Soft prompts. Are those different from regular prompts?
Think of it like this. With regular prompts, you're giving the LLM text. But with soft prompts, we're using these specially learned embeddings.
Huh.
They're like virtual tokens, optimized for a specific task.
So instead of words, we're using these embeddings to influence its output.
Exactly. It's like whispering suggestions rather than shouting commands.
I like that analogy. And you said there was another technique, P-tuning.
Yeah. P-tuning takes it even further. Instead of using fixed soft prompts, it uses something called an LSTM model to predict the best virtual token embeddings.
Wait, an LSTM model? Inside the LLM. That's like
Yeah.
a model within a model.
I know, right? It's pretty cool. LSTMs, or long short-term memory networks, are great at learning patterns and sequences. So in P-tuning, the LSTM is like a prompt engineer. It figures out the best way to, whisper those suggestions to the LLM.
So it's like having an AI whisperer behind the scenes.
It is. And what's really neat is that the LSTM parameters are shared across different tasks, so it's very efficient.
I could see how that would be a huge time saver.
Yeah.
Now, I remember you mentioned adapters and LoRa earlier. Do those work similarly to prompt tuning and P-tuning?
They all aim for efficient fine-tuning, but they go about it differently. Remember how we talked about adapter layers being like add-ons?
Yeah.
Well, adapters are kind of similar, but they're more like specialized modules inserted into the LLM.
So giving it new tools for specific jobs.
Yes. And they're trained right alongside the pre-trained model. So you're fine-tuning for a pass without mating with the original model. What's cool about adapters is they allow for continual learning and multitask learning.
Oh, right. Continual learning is like always adding new skills.
Exactly. It's like you learn to play the piano and you don't forget how to play the guitar,
Right.
right? And multitask learning, well, that means training on many tasks at the same time.
So it's like becoming an expert multitasker.
Yeah. Okay, so we've got adapters. Now what about LoRa?
Yeah, fill me in on LoRa.
LoRa stands for low rank adaptation. It's all about making fine-tuning even more efficient. It does this by adding these trainable matrices into the model, basically compressing those task-specific changes.
Like a space saver.
Yeah, you could say that. This makes LoRa really memory efficient, especially when you're working with huge LLMs. It lets you push the boundaries of what's possible with fine-tuning.
Makes sense. All of these techniques are pretty mind-blowing. But how do we actually use NeMo PEFT to put these techniques into practice?
NeMo makes it pretty straightforward. It's got Python scripts, APIs, all that. For training, you typically tell it where your LLM is, the data set you're using, and the PEFT technique you want to use. NeMo handles the rest.
Sounds pretty simple. And once the model is fine-tuned, how do we use it to make predictions on new data?
NeMo has separate scripts for inference. You load up the model, feed it the data, and then use the generate method. It really streamlines the process of using these powerful LLMs.
Okay, NeMo definitely seems like the way to go. But before we get too deep into PEFT, I remember you mentioned some techniques that go beyond traditional fine-tuning.
You're right. PEFT is great, but there are other approaches that can help us align LLMs more with, human values and preferences.
Right.
One of those is supervised fine-tuning, or SFT.
So still fine-tuning, but with a different goal.
Exactly. With SFT, you're fine-tuning on a data set that humans have annotated, so it's like giving the LLM explicit guidance.
So you're showing it examples of good and bad outputs.
That's a good way to put it. It's really helpful for tasks that are a bit subjective, like writing creative content or summarizing text. We're basically teaching it to mimic human preferences.
Interesting. And it sounds like instruction fine-tuning, IFT, takes this concept even further.
You got it. With IFT, we don't just give examples, we give instructions. We literally tell it what we want it to do.
So like giving it a set of rules.
Exactly. The idea is to make it more versatile. By training it to understand and follow instructions, it can handle more tasks, even ones it hasn't seen before.
That's a powerful concept. But I imagine training it to follow instructions consistently is tough.
It is. It takes planning, careful dataset creation, the right training methods. And speaking of training methods, remember I mentioned NeMo, RLHF, and NeMo guardrails earlier.
Oh, right. What makes them so special?
They address some of the key challenges in aligning LLMs with human values. NeMo RLHF stands for Reinforcement Learning with Human Feedback. Basically, we're incorporating human feedback into the training.
So we're bringing human judgment into the loop.
Exactly. We use that feedback to train a reward model, which then helps guide the LLM. This helps it generate better outputs, ones that are more aligned with what we want.
That makes sense. It's like having a supervisor. And what about NeMo guardrails? Are those like safety measures?
You could say that. NeMo guardrails give us a framework to set boundaries for the LLM. It's all about responsible and ethical use.
I can definitely see the importance of that, especially as LLMs become more and more powerful.
Right. So, for example, you might want to prevent the LLM from generating offensive content or spreading misinformation. Or you want to make sure its responses are accurate and, fit a certain set of values. NeMo guardrails let you do that.
That's crucial for building systems that we can trust. Now, you mentioned a P-tuning demo before. Can you tell us a little more about it?
Of course. In this demo, we're using the GPT-3 5 billion parameter model. We fine-tune it with P-tuning for two different tasks: extractive question answering and sentiment analysis.
So we're showing how it can adapt to multiple tasks.
Yeah, and we're using the same prompt model for both tasks. It really highlights how flexible and efficient P-tuning is.
So it's like it can switch hats and become an expert in different things.
Exactly. The demo uses Python scripts and configuration files. NeMo provides those. They handle everything: loading the model, preparing the data, fine-tuning, evaluating the performance. It's all there.
Sounds easy to follow.
That's the idea. And the results are great. The demo shows how much P-tuning can improve performance without needing a ton of resources. It's a good example of how PEFT is making LLMs more accessible.
It's amazing how much we've covered, from the basics of LLMs to all these different PEFT techniques.
It is. This field is moving so fast. And with NeMo, it's easier than ever to work with these models.
I completely agree. But maybe we should pause here for a second. Let our listeners catch their breath.
Good idea. We'll be right back to wrap things up.
Welcome back to the Deep Dive. We've been exploring these incredible large language models and how techniques like PEFT are making them so much more accessible.
It's been quite a journey. We just talked about that P-tuning demo, right? Really shows how you can fine-tune one LLM to be an expert in different tasks without having to retrain the whole thing.
It's amazing how P-tuning lets it switch gears like that, to tackle question answering, sentiment analysis, all seamlessly. And what really struck me was how transparent the demo was.
Oh yeah, the configuration files, the Python scripts, they give you a clear view. You can actually see how the training and inference work.
Yeah, no black box here. You can see what's happening. That's valuable for anyone who wants to learn from it and build on it.
Absolutely. Transparency is key, especially in AI research like this. And the demo, it's so well structured, makes it easy to reproduce the results.
It's like a blueprint for fine-tuning LLMs.
I couldn't agree more. So as we wrap up this deep dive into LLMs and PEFT, I want to leave you with something to think about. We've seen what these models can do, how we can fine-tune them, but what about the future? Where do we go from here?
That's the big question. What are your thoughts? What's next for LLMs?
Well, I think one thing's for sure. They're going to keep evolving. They'll get bigger, more powerful, more integrated into our lives. And that means these PEFT techniques. Even more important, we need smarter ways to work with these massive models.
So it's not just about size, it's about making them more adaptable.
Exactly. And as those PEF techniques get better, who knows what we'll see? Intelligent virtual assistants that really understand us, creative tools that can collaborate with us, maybe even personalized learning that adapts to each student.
That's a pretty exciting future. I'm really optimistic about what we can do with LLMs, especially with tools like NeMo and the research happening in PF.
It's an amazing time to be in this field. And thanks for joining us on this deep dive. Hope you found it insightful.
I definitely did. It's been great exploring this with you. Until next time, keep learning and keep diving deep into the world of knowledge.